Today, I'm going to show off one of several great things you can do with the apply operator. Welcome to this video on the apply operator. My name is Kevin Fiesel, and I am the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, which happened to be the first video in this series, I described how the apply operator in T-SQL functions and showed off the original use case for this feature. Let's quickly go to the classroom and continue the lecture part before we move on to our demo for today. As a quick reminder, the original use case for the apply operator was to execute a table-valued function for each record in a dataset. On the whole, I'm not really a big fan of table-valued functions to begin with, so that's not going to do it for me. Fortunately for the apply operator, it turns out that there is a much more powerful use case: ad hoc functions. Instead of creating a function, you can simply inline the contents of your function call into the apply, similar to how you would create a correlated subquery. This is important because it helps us solve a critical problem that SQL Server's optimizer has when it deals with functions. It usually does a bad job of estimating how expensive function calls will be, and thus usually generates a bad plan. Additionally, there is some minor overhead to executing a function call in SQL Server. That overhead isn't very much when you call it one time, but if you have a dataset with thousands or millions of rows, you will absolutely feel the pain. In this example on screen, I use the cross-apply operator, and then, instead of naming an existing function, simply use open and close parentheses to define that this is an ad hoc function. I don't need a name for the function, though I will require an alias. Inside the function, I can put whatever T-SQL is valid within a correlated subquery. Incidentally, if the term correlated subquery doesn't make much sense to you, here's an example of one. The term has two components: subquery and correlated. A subquery is a query within a query. That is, it's a valid T-SQL select statement that exists within another valid T-SQL select statement. The other term, correlation, tells us whether the subquery can exist on its own or if it requires the base query. A correlated subquery refers back to the base query, and thus you cannot run it on its own. In this example, our subquery references c.companyID, which ties back to the table company in the base query. For this reason, I could not run the subquery on its own, and thus the subquery is correlated to my base query. Similarly, an ad hoc function in apply may be correlated to the base query, or it can run independently. It's rare that you would have an independent query in your ad hoc function, though, because that would imply that your function does not have an input variable, and this would be kind of weird. Possible, but weird. Going back to the performance overhead of user-defined functions, ad hoc functions we create using the apply operator don't suffer from this cost. In addition to that, the optimizer often does a better job of picking the right execution plan. For this reason, simply inlining a user-defined table-valued function into an ad hoc function might be a performance improvement on its own, even without making any query or index changes. I'm not going to guarantee you a performance boost, but I will say that I've seen it happen quite a few times. I've shown you a quick demonstration of what an ad hoc function using the apply operator looks like. Now let's go to the demo and see one reason why we might want to use this syntax in our queries. Here we are in Visual Studio Code. I have a script open with a few variants on a simple theme. The theme for this video is going to be around product sales. Specifically, we're going to look at the number of times a particular item shows up on a customer invoice. I won't bother taking you through the wide world importers database schema and digging into that schema, so instead I'll provide you with a perfectly functional query. This query drives from the stock items table, as we're going to filter on the stock item name, searching for a particular type of extra large plush slippers. We are going to pick up the supplier name from the suppliers table. We'll get the package type name from the package types table. And finally, we'll get the number of times this has shown up on an invoice from the invoice lines small table. If you're playing along at home, I should warn you that the Wide World Importers database doesn't have an invoice lines small table by default. Instead, I have a script that takes the default data from invoice lines and loads it into invoice lines small. Then I add a huge amount of additional data to invoice lines. This will be particularly important to know in this series, as the relative value of the apply operator will sometimes depend upon how much data we're shoving through. Though I suppose that is a minor spoiler for this video. Anyhow, I have a count function and several non-aggregated columns, so to wrap things up, I need a group by clause with my non-aggregated columns. I'll run this query and show you that it does work. There's nothing inherently wrong with this query, but it's not the only way we can write the query. Let's see how we can use the apply operator to write this query. Scrolling down a bit, we can see the same base tables as before, at least up to the invoice lines small table. Instead of an inner join here, we are performing a cross apply. Then, inside of the cross apply operation, we have an ad hoc function that counts the number of invoice lines for a given stock item ID. We alias the results of this ad hoc function as I. Note that the count star function is inside of our cross apply operation. Thus, when we pull the result out as number of invoice items, we do not need a group by clause. The reason is that we will only have one row per stock item coming from the function. Let me run this query and make sure that it works. It does, and we get the same results back as before. There is another way of writing this query as well that I want to mention, and that is the correlated subquery approach. Here, instead of using the apply operator and performing our aggregation in the base of the query, we generate a new column as the result of a subquery. Once again, we get the count of records from the invoice lines small table for some stock item ID and return it as number of invoice lines. Because we perform the aggregation function within the subquery, we do not need a group by clause. And if I run this, we'll get the same output as well. Avoiding the group by is all well and good, but does it actually benefit us? To find the answer to that, I'm going to copy these scripts and then switch over to SQL Sentry Plan Explorer. In a new plan window, I'll paste in the text of these three queries. Then I'll select Get Actual Plan and make sure that I'm pointing to the Wide World Importers database. Once I know that's good, I'll select Connect, and I'll let these queries run. Because these are small data sets, it should only take a moment to get our results. Now we have 3 execution plans and results to share. Looking first at the statements and stats, we can see that all 3 queries finished rather quickly. In my pre-recording tests, I was getting back results in about 3 milliseconds of duration for the first query and 1 millisecond of CPU for the other 2. All 3 require 14 reads, as there is a good index on this table that I can use. Now let's dig into the execution plans. For the first plan, we drive from the stock items table, as we have just one row for a particular set of slippers. We do a key lookup to get the other information we need for this query from the stock items table. Then we join to the suppliers and package types tables, getting back one row from each. Our next stop is the invoice lines small table. We know there are 1,060 rows coming back, so our nested loops join runs 1,060 times. As a quick reminder, think of a nested loops join as a pair of for each operations. For each row in the outside table, get the set of rows from the inner table. Then, for each row of the inner table, emit the results of the join. We have one row in the outer table and 1,060 in the inner table, so we perform this work 1,060 times, sending back 1,060 joined rows. We then use a stream aggregate, the count function, to smoosh those back down to one row, which is what we send to the user. All in all, this isn't a bad query. It only takes a few milliseconds to complete, has indexes to support everything, and probably isn't going to bog down your server, even if it's running very frequently. But it turns out that we can do better. Here's the execution plan for the apply operator. It starts out the same as before, driving from the stock items table. Everything through the nested loops join connecting to the suppliers table is exactly the same as before. But with that next loop, things change. You see, what happens here is that for each row in the outer table, we're asking for a stream aggregate of all rows in the invoice line's small table. Because we are aggregating inside of the loop, we take those 1060 rows, smoosh them down to one, and then perform a join of one row against one row. This is more efficient in terms of CPU utilization, which is why our duration is shorter. But it takes exactly the same number of reads from pages, as we still need to get the same set of rows. There's no shortcut here to reduce disk utilization. And if I look at the correlated subquery version, the execution plan is the same as what we have for apply. In this scenario, both queries point the query optimizer in the same direction, and we end up with the same execution plan. Okay, 3 milliseconds versus 1 millisecond isn't exactly a wild difference, but as I hinted at earlier, record counts matter. For the next test, let's continue looking at the invoice line's small table, but instead of getting back just one product, we'll return any product with slippers in the name. Just as before, we'll have 3 queries: a query with the aggregation after the join, a query using the apply operator, and a query using a correlated subquery. Let me copy all 3 of these and then head back to Plan Explorer. In another new plan window, I'll paste these 3 queries and run them against wide world importers. This time, in my pre-recording testing, it took 9 milliseconds for the aggregation query to run versus 2 milliseconds for the other 2 competitors. All 3 queries required 223 reads, so there's no I/O difference. Looking at the query plan for the normal aggregation query, we can see that we scanned the stock items table to get our 20 records. There's a yellow exclamation mark on the operator, and if I hover over it, I can see that we actually read 227 rows instead of 20, as we don't have a good index that would support quick retrieval of just the records with the word slipper in the middle. We'll ignore this for the comparison, as we're going to have this pop up in all 3 query variants. But just as before, we see our first 2 nested loop joins are quite efficient. But now we have 21,165 rows coming back after we join to invoice lines small. For each of the 20 stock items, we retrieve any invoice line rows associated with that stock item. Then, for each invoice line item, we omit the combination of the stock item and invoice line item, which is how we get to 21,165. The stream aggregate groups things together by stock item name, leaving us with 20 rows again, which is what we send back to the end user. For the other 2 query variants, our execution plan looks the same as before. We have 20 rows going into the nested loops join. Then, for each of those 20 rows, we ask for any rows associated with that stock item. We get those rows, aggregate the results with the count function, and return that count for the stock item. It turns out that SQL Server quietly converts our ad hoc function from a row-by-row operation to something that only needs to execute one time. Thus, our plan is exactly the same as the correlated subqueries, and both of these are a little bit better than our original idea. But once again, we're limiting ourselves to the tiny amount of data we have available. The entire invoice line's small table has just over 228,000 rows in it. That's hardly enough to notice when you have good hardware, so let's kick things up a notch. I'm going to query against a table with 1.75 million rows, the invoice lines table. This first query looks almost exactly the same as our prior post-join aggregation query, except that we're hitting invoice lines instead of invoice lines small. Let's copy this as well as the apply and correlated subquery variants, and then we'll go back to Plan Explorer once again. Opening up one more new plan window, we'll execute this trio of queries and see how they do in comparison to one another. Now we're starting to see a more significant difference. With 20 items relating to slippers in the table, we can see that there's starting to be a significant difference between our first query and the other two. In my pre-recording testing, the first query took 79 milliseconds to run versus 14 milliseconds for the other two. And looking at these execution plans, it's basically the same as before. For the query in which we aggregate after a join, we're pulling back 177,534 rows before aggregating it back down to 20. But for the other two queries, we pre-aggregate and end up requiring significantly less CPU time to run. The ability to pre-aggregate function results is just the first of several great use cases for Apply. We saw how we could reduce the CPU cost of certain classes of query simply by moving a large aggregation out into a separate subtree in our execution plan, allowing the query optimizer to aggregate the results first and then join one row instead of a larger number. With larger data sets covering millions or hundreds of millions of rows, pre-aggregating in the query can save us a significant amount of CPU time. Though, as we saw, it doesn't change the number of reads we need to get our data. We're still going to absorb the cost of reading data regardless of when we aggregate. But I hope you'll agree that the apply version is a more efficient query overall. In the next video, I'm going to show you another great use case for the apply operator: finding child records. We'll have links and show notes in the description below. And until we see each other in the next video, take care.